Hello, everyone. My name is Alberto Rodriguez, and this is Robotics Today, an open series of technical talks in robotics. I'm happy to be here to introduce the kickoff of this series with Andrew Davison. But before that, whoever you are, wherever you are, we hope that you and your loved ones are doing well and staying safe. COVID has challenged the way we live and the way we work, and the way we relate to our communities, including robotics. And sort of that constraint has given us a great motivation to try to explore the online format and see how much we can get out of it. For all of you, those of you that are listening right now, thank you. If you're not, we're recording all these and we will make the video available in YouTube later on. So without more delay, I'm pleased to introduce and welcome Andrew Davison joining us, I'm guessing from home, I don't know. Before that, I want to welcome also John Leonard, who will be with us in the panel discussion after Andy's talk, and who we've asked to prepare a spicy question to kickstart that panel discussion. So we are looking for that, John. Thanks for joining from MIT. As many of you might know, Andrew, he's a legend in the perception community. He's a professor of robotics vision and director of the Dyson Robotics Lab at Imperial College London. And he has developed several perception systems that have been widely adopted by a big part of our community. Maybe MonoSLAM and Semantic Fusion are the most famous ones. And he has also deployed some of his algorithms in real robotic systems, including intelligent robot vacuum cleaners. But most of all, I would like to highlight a couple things from his trajectory and the large influence that it has had on many of us, right? So on one hand, Andy has been able to keep up with the huge transformation that sensors have had in the last couple decades, right? So if you look at the two most influential works or the two most cited works in his career, MonoSLAM and Semantic Fusion, they derive from very different sensors, and somehow Andrew has managed to stay at the forefront on both ends of that transformation, which is quite remarkable. And maybe the second thing is that Andy has also walked us through another transition that the perception community has undergone in the last 2 or 3 decades, going from maybe a more narrow, slightly narrow perspective, a geometric perspective on what perception is, to a more or broader sort of semantic understanding of what perception is, or what how he calls it, spatial AI. So without more delay, Andy, of course, the cliche, the long-standing cliche says that SLAM is a solved problem, but somehow stubbornly, it seems like it remains to be a solved problem. How is that? Why is that, Andy? Thank you for joining us.
Thanks very much. Yeah, so it's a problem that I think has continued to evolve into more and more interesting and challenging areas. So as you mentioned, sensors change, different sorts of, the background algorithms and tools change, and our goals in applications change. And, one of the messages I want to get across in the talk is that I see SLAM as a rolling problem that's always changing into something even bigger. And that's what I'm now calling spatial AI.
Excellent. Thank you.
So I'll share my screen and start. Yeah.
Yeah, go ahead.
Okay. Yeah, sure.
Your show.
Just give me a second. Okay, so my slides are coming through okay? Good. Okay. So thank you very much for the introduction, Alberto. Thanks to all of the organizers of this fantastic new series. So of course, it's a great honor to be invited to be the first speaker, and I'm excited to watch the rest of the talks in what look like it's going to be a great program. Thanks also to John for joining the panel. So John's someone I've known and followed his work, right since the time of my PhD. Okay, so my talk is called From SLAM to Spatial AI, and I've already said something about what that means. So I'll go into a bit more detail on that. I'm going to talk a little bit about a little bit of history, not too much, a little bit about my general thoughts about where this whole field is heading, and then also show you, various examples, in particular from recent work in our lab, of systems that I think are representative of progress in this area. So let's start by thinking about what's actually out there at the moment. So having worked in this domain now for over 25 years since I started my PhD, when working on SLAM using vision was really just a bit of an out there research idea, we've now reached the stage where visual SLAM is actually present in a number of products that you can actually buy. So I've shown a selection of them here. Some of these are certainly what we would think of as robots. So the Dyson robot vacuum cleaner I'm showing there. Drones, such as from companies like DJI or Skydio. These run visual SLAM systems for localization and mapping. But then there are also a lot of other devices that we might not think of as robots. So inside mobile phones, there's software like ARKit or ARCore that enables positioning and real-time mapping on those devices using cameras and other sensors. And then this emerging area of headsets for virtual and augmented reality. These are also SLAM-enabled devices. So this is, kind of an amazing thing to me that this technology is really getting out there now. But if we look at what's actually in products like this, it's mostly at the moment positioning and perhaps sparse or semi-dense reconstruction. That's the technology inside these products. So there's more and more levels of technology gradually coming in. So things like dense and semantic mapping that I'll talk about later, based on vision, are also entering these products. But I think it would be fair to say that these are all still relatively, early sort of products out there on the market. So one way of thinking about SLAM is to think of gradual progress in terms of adding levels of capability. So this is a picture that comes from our startup SLAM core, where we really think of levels of capability in SLAM from localization up through dense mapping and then eventually to semantic understanding. So I think of SLAM as this really, rather than saying SLAM is something that's done and then these levels sit on top, for me, all of this is SLAM, and it's gradually evolving into a bigger system. And for me, that's a valid way of thinking about it, because I always come back to SLAM-like ways of thinking whenever we're trying to add these new layers. So every time you add a new capability, it may affect, the ability of the robot to localize, for instance. So I see it always as a kind of closed loop. And hence my argument that SLAM is evolving into something bigger, spatial AI, which I define here as the online problem where vision is to be used, usually alongside other sensors, as part of the AI, which permits an embodied device to interact usefully with its environment. So really, we're thinking about embodied spatial AI in a general sense here. So where might that take us in the longer term? So I've just got a couple of ideas here of products we might imagine in the longer term. And the first one here is in robotics. And I should first say very clearly, this is just a mocked up image I found somewhere on the internet and is certainly not representative of any products that are specifically under development. But let's imagine this product, a mass market, general purpose household robot. So it may look nothing at all like this, probably won't look humanoid at all, I strongly expect. But its job is cleaning, tidying of complicated rooms and objects, and it's going to need a spatial AI system that gives it all the perception that it needs to do all of that. But let's bear in mind that the system that it has will be constrained by price, aesthetics, size, safety, power usage, and all these things which must fit within the range of a consumer product. Here's another product that I think could really be a breakthrough. And note that I've called this a spatial IA product. So this is a rather cute inversion of AI to stand for intelligence augmentation. So I think of this as a sort of intelligent device, but that's designed to work with a human in the loop. So this is a concept for a future augmented reality system with a form factor of a standard pair of glasses. It provides a robust and accurate real-time overlay and spatial memory of all places, objects, and people. But it has very, very strong constraints on how it can work. So I think for this to really change the world, it may have to weigh 65 grams and have all-day battery life. So I'd like to make the point that, I think both of these two types of products, they probably require quite similar capabilities from a perception system. I think either of these products would have a massive impact if they existed. The reason they don't exist yet is not because there's no demand, but because no one yet knows how to build them, and especially within those very strong constraints of real products. So I've just got a sketch here of how far I think we've got to go. We've got current products on the left, we've got current research prototypes happening in labs, and then we've got this big, big gap to where we really need to get to this full spatial AI performance within the constraints of practical devices. And I think we're talking about orders of magnitude of progress needed. So thinking about this concept in general of spatial AI, so I think it's perception for embodied intelligence. I've written recently a kind of discussion paper about this whole topic that anyone might be interested to read. So it's called Future Mapping, the Computational Structure of Spatial AI Systems. It kind of defines more about what I understand this problem to be. It makes a few hypotheses, and the key hypotheses are along the lines that a spatial AI system should build a persistent and understandable scene representation, which is somewhat close to metric 3D geometry, at least locally. Within that, it will contain hierarchies of lower level geometric information and higher level semantic information. And I also think there's a generality to spatial AI systems. So whichever of these applications this might be ultimately useful for, I think there'll be a lot of commonality between the systems, and maybe a fairly small number of performance measures that define the differences. So I also think that by working on this topic with the main goal of actually developing products, we may learn a lot about general embodied intelligence. I think that's something very interesting to discuss. So what are the kind of computation and storage patterns that are required to do embodied intelligence efficiently? So that's, I think, interesting general research on AI and intelligence. So I'm going to move on to a little bit of history here. So really to guide you a little bit through these levels of progress that I've talked about in SLAM. So just very first, briefly, so probably John may be the only person here that actually remembers this work. But this was my PhD work, which was in the Active Vision Lab with David Murray in Oxford back in the mid-90s. So I worked on what turned out to be one of the very first visual SLAM systems. So this was a stereo active head with 2 cameras mounted on top of a mobile robot platform. And we were able to achieve localization and mapping with this system by having it drive around and map a set of point landmarks in a scene. So on the right, you see a picture of the estimated trajectory of the robot and the estimated positions of a set of landmarks that it's built into a map. And this was all running in a Kalman filter for joint estimation. That led, after a few years, onto the MonoSLAM work. So let me just quickly show you a video of this. So this was really inspired by saying, let me just go back a second. So it was inspired by saying, can we do SLAM with the simplest possible vision-based hardware setup, i.e. a single handheld camera moving around in a room with no other kind of sensors and ideally no prior information about the room. So the goal is to localize this camera in 3D as it's moved around in a general way in real time and to build a map of the scene that it sees. So here you'll see the camera's view of the scene, and you'll see that what's going on here is we're detecting and tracking a set of landmark features in the scene. And so these are salient points in the scene, and we're building them incrementally into a persistent map. So if I just skip forward slightly here, you'll basically see the result of that. So this is the real-time 3D estimated map of the scene, where the box flying around is the estimated position of the camera, and each of these patches is an estimated feature in the world with a 3D ellipsoid. So this is a sparse feature-based map of the scene, and really you'll see that we're not getting much information about the scene here, but this is a map of the scene which is enough to enable localization of the camera. So the main thing we're interested in here is where is the camera, and this is a map that's sufficient to do that. So that system, or something very much based on that, is what enables the SLAM capability in the Dyson 360i robot. So around the time of MonoSLAM, I first met some of the researchers from Dyson, and we decided to work together on what seemed like a very ambitious concept at the time of building a product that did visual SLAM, and that eventually led to the release in 2014 of the Dyson 360i robot, which performs monocular SLAM. So a few years after that, and now we're talking around 2010, I think there was the next big kind of advance in real-time visual SLAM systems, and this is the arrival of dense SLAM. So the goal here was now starting to switch towards, we're doing pretty well on positioning a camera. How about this next thing of getting more significant detailed information about the scene? So can we actually build these really detailed scene representations where we can see the shapes of objects and so on? So in particular, an important person in this was Richard Newcomb, who was a PhD student in my lab at the time. And he worked on several very influential systems, including DTAM, which was a system just based on pure RGB images and was able to do dense real-time mapping. And then the other important one was Connect Fusion, which used a Connect camera. So what's really interesting here is it was the arrival of certain commodity technology that made these kind of things possible. So in particular, GPU, so general purpose graphics cards that were programmable to do computer vision-like things are behind all of the parallel processing that you need to do this kind of real-time dense visual SLAM. And then, of course, depth cameras and especially Kinect. And it's hard to remember now what a kind of revolution that was when it came along. So depth cameras had existed before 2010, but they cost thousands of dollars and they weren't very good. And suddenly you could buy this thing for $100 that was great. So Richard actually was doing an internship at Microsoft Research just as the Kinect was about to come out, and was able to work on that and really see what can you do in real-time SLAM if you have a stream of pretty high quality depth information. So just to show you a video that's representative of dense SLAM systems, this is a system called Elastic Fusion, which was work from our lab, the Dyson Robotics Lab, about 5 years ago, led by Tom Whelan. So here we see a real-time dense SLAM system here. So the input to this system is what you can see in the bottom left. Let me just full screen this. So in the bottom left, you've got the live kind of image stream from a color camera and the live depth stream from a Kinect depth measurement. And then what we're doing is both tracking the camera and then fusing all of the information into a dense scene model in real time. So there's many possible ways to represent dense scenes. In this particular system, we're using a representation called circles. That means that the representation of the scene is basically a cloud of little disks. So these are points that also have a kind of orientation and a size. So they're representing small disks. And if you kind of smush enough of them close together, it looks like a continuous surface. So that's one of several options for representing dense geometry. A particularly nice point about the circle representation is fairly efficient, and that enables Elastic Fusion to do loop closure. So this means that when the camera comes right round and revisits old parts of the scene, it's able to make corrections to the map so that the map stays consistent, which is something that wasn't possible, for instance, in the original Connect Fusion system. So I think the next and probably the most recent sort of real advance in real-time visual SLAM is what's very much going on at the moment, which is trying to add a semantic layer. So the map built in Elastic Fusion, it's very detailed, but it's still just raw geometry. In the end, it's a cloud of points, so there's no meaning associated with it. So you know, from 3 or 4 years ago or a little longer ago, of course, the big kind of new technology coming into SLAM is deep learning. And so enabled, of course, also by GPUs, this capability to do real-time labeling and recognition. So we built a system called Semantic Fusion, which is aiming to do dense semantic mapping of a scene. And if I show you this video, this is what we're trying to achieve. So map a scene densely in 3D, but also apply labels to it, which represents our best estimates of the objects or type of objects that are present. And the way that this system works is actually fairly straightforward. So we have our input data stream of color and depth images. They're fed along 2 piped ways. One does SLAM reconstruction. So this is in fact Elastic Fusion, what you just saw before. It also feeds those frames to a CNN, which has been trained for per image semantic segmentation. So it labels every one of these input images with an estimate of what are the identities. And then what Semantic Fusion does is fuses those labels into the dense map. So every circle in the scene is being labeled with each circle in the scene basically holds a distribution over what it thinks the most likely labels are for that point of geometry in the scene. And the interesting point of doing this in a SLAM style is that the label for each point in the scene can gradually change and improve. So from one point of view, you might get not a very good labeling of a particular element of the scene. It's quite ambiguous. But when the camera moves to a better location, that can actually improve. Okay. So there's just one paper I'd like to mention in connection with that. So something that we've published or just will appear in the ICRA conference in the next month or so. So these systems that label scenes based on CNNs, I think there's 2 interesting ways to go about that. One is the view-based way that we took in Semantic Fusion. So you can label every view in a view-based way as the camera moves around, and then try and fuse all of those labels into the 3D representation. Another possibility that we're seeing a lot of nice systems based on is build the whole map and then use something like a 3D CNN that can take in that whole 3D map and try and label it in place. So there's very interesting pros and cons between those 2 methods. One is immediate; it gets to work on the raw data, whereas the other one gets to see the whole map in one go and can take account of whole context and that kind of thing. The computational characteristics of those 2 things are also very interesting, very interesting to study. So have a look at this paper here if you're interested in that. Okay, so we've got these this range of systems that have gradually got more advanced. One way of thinking about what happened there is that we've essentially been gradually throwing more and more computation at this problem, and we've seen progress because of that. So where does that actually take us? So is this useful steps towards this spatial AI goal that I was talking about? So I find this picture quite interesting. So this is actually a kind of more or less a mock-up that I did, but thinking about all of the computation that's happening in a system like Semantic Fusion. So it's a pretty complicated system. We've got data sort of represented in green, and then blocks of computation represented in yellow. And don't worry at all that this is a bit small to read. All I want to get across is this is pretty complicated. So there's labeling, there's tracking, there's fusion, there's map optimization. There's all kinds of things going on here. So how are we going to get this to run on tiny embedded devices that weigh 65 grams and this kind of thing? That's what I'm really wondering. How are we going to kind of optimize this graph down to something a bit more manageable? So I think there are two kind of interesting lines of attack that we've been following in our lab, and which I'm going to take you through next. So one is to really think about representation. So this really means if you look at something like Semantic Fusion, we've got these huge representations of detailed things, like we've got image maps of labels, the size of an image with hundreds of thousands of entries. We've got maps of circles. So I think the map of the room that I showed you in Elastic Fusion earlier has something like 5 million circles in it. So we've got lots of big amounts of data moving around this graph, being worked on, parallel computation where we can. But if we, the current implementation of a system like this is also, some parts of this work on a GPU, some of it's running in CUDA, some of it's running probably in TensorFlow or PyTorch. Other significant parts are still running on a CPU, a lot of data transfer and so on. So what if we could kind of simplify a lot of those representations? So can we turn these huge, dense blocks of data into much more simple things? Then we seem to get to something which would be much more efficient. The other line of attack, which I'll talk about a bit later on, is can we use custom computing hardware to help us with this? I'll come back to that later. So firstly, thinking about representation, we've done various bits of work in our lab, and most of this has increasingly been using elements of machine learning. So we're really trying to say, are there representations or algorithms within our complicated SLAM systems which can be replaced by something learned, which will have kind of simpler and probably more generally abstract and interesting properties. So that brings me to a general discussion, which I'll try to tackle briefly, about SLAM and deep learning. So I think everyone working in SLAM has been thinking a lot about this in the last few years, as in most fields of AI, of course. My point of view on it is that we have a kind of sliding scale here, almost a continuum between things we could do, where on one side we've got fully hand-designed algorithms, and certainly the early systems that I showed you, purely geometric systems, they're completely hand-designed, MonoSLAM or Elastic Fusion and so on. At the other end of the scale, we've got this possibility of fully end-to-end learned algorithms. So I think if you speak to someone, let's say at DeepMind, they'll probably tell you, or they might believe that why would we ever hand design anything, any part of an algorithm? Why don't we just learn everything end to end? And I'm not saying that they're wrong. I think in the long term that may well be exactly right, because every time a human designs representation, you put some limitation that an artificial system may not need. But I think that the way that almost all of us are proceeding in trying to build systems that work is a modular combination of hand-designed elements and learned elements. And I think there are two key ways to do that. Either we can start with our hand-designed system, maybe the one I showed you in the graph just before, and replace some of those blocks with learned things which work better, but also maybe have some sort of abstraction and efficiency. The other is to start off with a big neural network and say, this is my system, but gradually kind of impose structure on that network and say, is this not a completely general perceptron? It's, there's structure, there's things like spatial transformers and so on in there, which force it to do certain things. I see those things as very similarly related and will ultimately meet in the middle. Okay, so let's, so having said that, let's talk about some of the work we've been doing on representation in our lab. So the first sort of category of projects I'm going to talk about was started by a paper we had called Code SLAM back in 2018, and was followed up closely after by a paper called Scene Code. So don't worry too much about the details of this kind of network diagram I'm showing you here, but the key idea is that we want to encode the variation in dense depth that we can see from a a single camera in terms of a way that what are the main variations there. So if you just think of a dense depth map, in principle, at VGA resolution, that has 300,000 parameters for the depth at every pixel. But if you point a camera around at real scenes, there's actually a lot less variation than that. So most real scenes tend to be made up of continuous objects and surfaces. So there's a lot of sort of structure in the space. So in Codes SLAM, we do some machine learning. We have a data set of in fact synthetic indoor scenes that we train this on, and we learn an autoencoder which is able to go from a sort of small bottleneck to generating likely dense depth maps. So with a fairly small encoder of maybe 32 parameters, we can describe the variation that tends to be present in dense depth maps. So there's more details to it than that, but what that essentially enables is when you have a camera moving around a scene, from each single view, you can make an initial dense depth prediction, but as the camera continues to move, you can then optimize multiple dense depth predictions against each other. So by optimizing the codes of two of these dense depth maps, we can adjust them to try and bring them into alignment, but we will only be adjusting them within the space of things that we think are feasible given our data set. So let me just show you a video here. So in fact, we've recently published a paper called Deep Factors, and there's real-time open source research code available based on this paper, which is an implementation and extension of the Code SLAM idea into a more general SLAM system. So just to give you an idea of how this works. So remember that in this system, we just have a monocular camera. So there's no depth camera in this system. So as the camera moves around, you'll see that every few frames, we add in a new part to this representation. So we've got a new keyframe. We immediately get a dense depth kind of single view depth prediction from that frame, but then we're able to optimize it against the other nearby frames to try and produce a larger and more consistent overall 3D map. So we're able to do jointly optimizable dense visual SLAM within this coded subspace, and so just from monocular video input. So of course, subject to the things you would normally assume about a system that includes machine learning, that it will work fairly well within the scenes that are similar to the scenes that it was trained in. But please have a look at that and try the code out if you're interested. I'll just very briefly show you this and the other video. So this is from the scene code system. So this is showing that we can use very much the same idea of code optimization, not just to deal with geometry, but also to deal with semantics. So here we have a video where our goal is to jointly estimate both the dense depth of this scene and also the semantic labels. But the way that we're basically combining multiple views now to do label fusion is not like in Semantic Fusion, where we were just doing per pixel averaging pretty much, which gives us sometimes this quite noisy looking results. Here we're doing label fusion by code optimization. So the labels in each view are able to change, but they will only change within the space of feasible things that we are familiar with. So therefore, they'll tend to change in this much more sort of smooth and coherent way. So it will tend to change the label of a whole region, such as an object, for instance. Okay. So those systems use learning to kind of encode the variation that's present in a whole scene. But you can see that there are some limitations there. In some ways, maybe we're asking learning to do too much there, because a fairly, a small encoding cannot give us that much accuracy in representing a whole scene. So what seems more sensible is to focus learning down on things like objects. So going back to about 2013, we've been interested in this idea of, can we actually build SLAM maps where the objects actually really are the map? So this system called SLAM++, it was this idea that we would come into a scenario where we're going to be moving a camera around and trying to map a scene, but we're not going to do bottom-up mapping of this scene and then try and fit semantics and objects later. We're going to have a database of the objects that we expect to be present, and we're going to try and fit those as soon as we can. So as the camera moves around, the representation of the scene that we're building is a map that's directly built at the level of objects. So you'll see that the camera will move, and then down in the bottom right here, you'll see objects kind of popping in to this representation. So here, either an object is present or it's not present. There's no such thing as a sort of partially fused object. So this approach works in the case where the scene is obviously consists of a lot of instances of objects for which we have precise prior models. So here we have no ability to deal with objects that we don't know about in advance. So I'd just like to show this graph. So I think this idea of building maps out of these higher level abstract kind of concepts like objects, I think this fits very much in with a lot of thinking that's out there in the community at the moment, into building sort of layered scene graph type representations of scenes. So there's a couple of images here on the back on the left from Facebook Reality Labs, on the right from Luca Carlone's group at MIT on building, what I think is really the right direction in terms of layered scene graph type representations. So in our lab, we've continued to focus on object type representations. So let me show you a couple more things that we've done. So this one is called More Fusion. So this is a new system just about to be published this year at CVPR. So this is really a direct follow-up from, so let me just move to the right place. So really a direct follow-up from SLAM++, in that we are coming to a scene in the situation where we do have prior high-quality CAD models of the objects we expect to be present. But you'll see that here we're really turning our attention to what could actually be done with that, in that we're doing that now within a manipulation setting. So here we have prior CAD models of this set of objects. The camera now moves around, so there's a depth camera on the robot arm. The robot arm explores. It does some initial volumetric fusion of the scene, but then as soon as it's able to, it fits precise 6D pose of object models to any object it's really confidently identified. So here you'll see it just found this drill in the center of the scene. And then what you'll see on the right is then it really jointly optimizes the poses of all these objects. So we want to deal with really difficult situations where multiple objects are in contact, they're occluding each other. So it's actually pretty hard to do single object pose detection in that situation. But if we jointly optimize the poses of all the objects, then we can do it. So here is now an application of that for a kind of difficult grasping situation. So here what the robot wants to do is actually move the rather large red box in the middle of the scene into the brown box on the right. So first it's scanning the scene, it's fitting object models, it's jointly optimizing them, and then when it's confident, it decides on a plan of action. And it realizes that to get to the red object, it's going to have to move two other objects out the way. So first it takes this object here, drops it in the bin on the left, and then also this yellow box. And now it's able to get to the object that it's interested in. And this isn't just grabbing and dropping, it's picking it up in a well-known pose, and therefore it's able to then precisely place it exactly where it wants it to be in the box. So another system I'd like to show you briefly. So it's very much along the same idea of an object-based SLAM system, but in some sense at the other end of the scale here. So there we were saying we had a precise CAD model of every object we were going to see. This is kind of the opposite end, where we don't have any prior CAD models. We do have a really good neural network. So we're using mask RCNN, which is able to look at video frames and give us accurate masked regions of anything that it thinks is a separable object. What we do in this system is for every one of these objects that we detect, we add it to a SLAM graph. So that's what you can see coming out here now. So this is a graph of the positions the camera has been in and the positions of objects. And then each object, we make an independent fused 3D reconstruction of it. So pretty much Connect Fusion running in a little volumetric region for each of the objects. And then we've got each of these objects then really serving as a kind of landmark in an overall SLAM graph. And we can do normal SLAM things like loop closure. So here we've come all the way around the room. We find a set of objects that are consistent with a set of objects we saw earlier. We enforce those constraints on the graph and solve the loop. So this is a powerful system in that it can map all sorts of different objects in the scene, but it has the downside that it's only using the visible information. So when it reconstructs an object like a chair, it's only able to reconstruct the portion of that that it can visibly see. So that's at the other end of the scale of reconstructing, of estimating the pose of a CAD object. So the most recent work we've done in this space is really trying to find a space somewhere in between. So this system called MonoSLAM that we've also just recently put online is, just find the right place in the video. So we're saying that we're somewhere in between. So we're going to recognize objects in the scene, but for a particular class of object, we don't have a precise CAD model. Instead, we have a kind of warpable shape model. So this is a model that we've learned using a deep learning method. So it's a 3D volumetric autoencoder, which we've trained on a data set of 3D objects. So we've got hundreds of CAD objects of mugs and hundreds of CAD objects of bottles, and we've learned a kind of shape space model for each one of those objects. So now we can use those in a SLAM context. So there's lots of interesting work on this kind of idea of coded object models going on, especially in the computer vision literature. What we focused on here is can we actually now use these sorts of models for quite useful things in a SLAM context. So here you'll see that each of these objects in the scene, the first time that we observed it, we basically optimize over the coded parameters of the shape model of that particular class of object until the reprojected shape of that object matched well with the depth information that we've got. So just from one view or one depth view, we can get quite a reasonable estimate of the shape of the object. From multiple views, we can improve that even more. So this is now a full SLAM system where we are on each new depth frame, we're jointly optimizing for the position of the camera, the positions of all of the objects, and then also these shape parameters of the objects. And let me just skip forward a bit to show you an application of that. So we've also, let me just go to here. So we've also looked at robotic pick and place using this system. So here we've laid out a few of these objects on the table. We've got a depth camera on our robot arm. The depth camera scans the scene. In the top left, you can see it gradually fitting the object models to the scans. Once it's fitted the models, it can then do some simple planning and action. And here what it does, so it knows that there are 4 bowls in the scene, but it's able to accurately enough get an estimate of the size of the bowls that it picks them up in order of size, biggest to smallest, and then is able to place them in that order to stack them precisely in the box. So again, this is an example not just of picking up an object and dropping it, but picking it up in the situation where we've got a very accurate estimate of the shape of that object, and therefore we're able to place it very precisely. So we're really interested in this object-based representations of a scene, and increasingly in how those can actually be used for useful robotic things such as manipulation. The last thing I'll show you in that kind of area is work from the Dyson Robotics Lab called the RL bench. So this is a new benchmark simulator or data set which we've just recently put online. So this is also available as open source software. So we're interested in enabling robots to do many different things. So this is a data set where these are hand-designed tasks for many of the things we might imagine a robot arm might want to do, like placing objects, opening things, closing things, putting things on top of each other. And within this simulator, you can really do what you want. So you can run the simulator. It includes simulated cameras of various kinds, both kind of off-board and on-board. It includes simulation of physics. So for instance, you could train reinforcement learning agents to try and solve these tasks, and some people are trying to do that. But what we really wanted to do with this data set was make it deliberately pretty much out there in terms of what anyone's doing in reinforcement learning. This is an example, by the way, of domain randomization. So that's something that's been found to be very useful in a lot of reinforcement learning. So no one has shown reinforcement learning able to do these wide range of things, and reinforcement learning, I think, has mainly been successful for fairly sort of local and repetitive kind of tasks. So I would argue that maybe something more like a spatial AI SLAM-like object-based representation of a scene may be the sort of thing that may enable AI to solve tasks like this. So by putting this data set out there, maybe we can motivate more people to be interested in those kind of methods. Okay, so I mentioned earlier on that given this rather complicated looking computation graph, we needed angles of attack in order to really make this computation feasible, especially on embedded devices. And the first thing that we really looked at was different sorts of representation that might turn some of these things from huge blocks of data into rather smaller things like codes, for instance, representing objects or scenes. The other kind of key approach I've been very interested in the last few years is can we use new things happening in hardware to help us with that? So hardware as it relates to SLAM and spatial AI. So I'm not really talking here about actual robotic manipulator hardware. I'm talking about the sensing and perception hardware, and in particular the computation hardware that would be involved. So the main areas of interest are sensors and computer processors. So first of all, in sensors, so I've been very interested in what's been going on in cameras. So as Alberto mentioned earlier, I see computer vision as a broad area, and I would have always included, whether it's a single camera, a stereo rig, a depth camera, it's all part of computer vision. But that is an area subject to ongoing change. And the most exciting thing that I've seen in the last few years is event cameras. So this is probably something that a lot of you know about. So this is an image sensor that rather than capturing frames, it captures per pixel asynchronous differences. So the report from an event camera is a sequence of events, which is each pixel telling you with an accurate timestamp when it's changing its brightness. So as soon as I heard about this, I was immediately excited. First of all, because the data rate from a camera like this is much more scene dependent. So if there's nothing changing in the scene, then there's no events, and if there's a lot changing in the scene, there's a lot of events. So we worked on SLAM-like competencies using these cameras, and I'm not going into detail on this, but we managed to achieve monocular 3D SLAM with a single event camera. So here there's just a single event camera being waved around, and we're jointly estimating the color, so it's the intensity reconstruction of the scene, which is not something that comes by default from an event camera, the 3D motion of the device, and the depth of the scene. So that work is very much ongoing. There's lots of several labs now doing really nice work in this area. But for me, it's all about this. I think about this in terms of a computation graph, and this idea that this event camera does right in hardware on basically the sensor chip. It does a very important job for you. So you don't need to pipe video data down to a CPU because it's done some abstraction right there on the chip. And I think that's the start of a more general thing that's going to happen, where cameras will become programmable devices that are able to do a lot of processing right there, kind of within the chip. So the other big area in hardware is processors, and this is something I've also been really interested in, and really starting from, going back 10 years where I saw GPUs coming into computer vision and what a massive difference that made. I mean, I think everyone's familiar with that now with deep learning, that you need GPUs to do deep learning, but you also need GPUs to do dense SLAM. So the sort of computation where you want to do something at every pixel on every frame, and it's very parallelizable, GPUs are really good for that. So we had a project, this was joint between several universities in the UK over about 5 years, which was really about investigating how do SLAM algorithms work on different sorts of processors. So from a huge sort of desktop machine in the top left there with a big GPU down to a tiny embedded board. So can you pick apart a SLAM algorithm? Can you really think about which bits work well on which sorts of processor? And can you facilitate the sort of research on co-design of processors and algorithms? And of course, an obvious question there is, can we build a chip specifically for SLAM that's as efficient as possible? And that's a really good question. And there's been lots of nice work and some concrete projects on that particular idea. My kind of current thought about that is my thinking about SLAM is too broad at the moment to do that. And I think when I was taking part in this project, people wanted to pin me down and say, okay, what's the algorithm? And then we'll go and design the hardware. But I was always a bit like, well, there's a lot of possibilities and I'm not sure. So I wasn't willing to commit at that point. But then I heard about interesting things that were going on in kind of commercial hardware, and in particular graph processors. So the main workhorses of AI at the moment are CPUs and GPUs. Of course, these are processors that are very useful, but they're not really designed for AI or vision. CPUs are designed for general purpose compute, word processors, if you like. GPUs are designed for graphics. They've been successfully adapted for various things in vision, but as I pointed out earlier, we can use them for parts of a vision system, but very far from all of it. We generally have to have CPUs still around too. So a graph processor is a new idea, and in particular there are many related ideas here, but I'm going to focus on a company in the UK called GraphCore that's got a product called the IPU, or Intelligence Processing Unit, which is a new processing chip which is designed to particularly enable what they think are the important workloads in AI. So what a graph processor is a massively parallel chip. So an IPU has about 1,200 processing cores on it, but they're quite different from the cores on a GPU. They don't all have to be doing the same thing in lockstep parallel. They can all be running very independent programs, and they're able to have very high bandwidth and almost arbitrary connectivity for message passing between them. So what they're really good at is processing graph-like workloads, so ad hoc kind of arbitrarily shaped graph-like workloads. And really the sort of processing where the computation and the storage is really kind of mixed together. So for an IPU to work well, you don't want it to be pulling any data from external memory. You want anything that it's interested in storing to be stored in a distributed way, kind of alongside all of the cores of this processor, and then to talk to each other by passing messages. So that's very interesting. I can immediately see, this can reduce the sort of data flows. So the things that make, processors use a lot of power are generally moving memory around. Bits times millimeters is what you want to reduce. A graph processor, by really thinking about jointly reasoning about processing and storage, can really tackle that. And yeah, there's a lot of technical detail, but an IPU devotes a lot more of its area on the chip to memory, which is all about communication and local storage, than logic, which is about fast compute. So the actual cores on an IPU are not individually that fast, but they're very, very well interconnected. So that enables new styles of algorithms. So when you compile something for an IPU, and this is a visualization from GraphCore, you have a a computation, and they're particularly focused on optimizing neural networks. So this is, I think, AlexNet actually. You take all the computation involved in training or using AlexNet, and you think of all the elementary sort of computations and data movements that have to happen, and you compile it down onto the grid of processors on an IPU. And this is a kind of cute visualization that shows something about all the connectivity, and you can identify the kind of regions in the neural network. So having seen that, I started to think, well, could we do spatial AI in a similar way? So, you know, this is really preliminary thinking, and there's a lot more detail in this paper I mentioned earlier, if you're interested. But let's think about all the computation involved in a spatial AI system. We've got a real-time loop doing things like tracking and labeling. There's clearly a graph-like structure there. We've got our cameras, which are kind of sending data. There's clearly sort of graph-like structure there in the regular pattern of pixels and so on. And then we've got our kind of map store. And anyone who's worked in SLAM for a while knows that, you know, graphs of how different nodes and factors connect to each other are really the best representation for SLAM. So there's graphs everywhere in SLAM. So can we really map those graphs onto a processing chip and then use that to implement possibly, you know, some steps towards this very efficient vision of spatial AI that we think we need for products. So we've taken some first kind of concrete steps in the last few months, and we've got a paper to appear at CVPR, which is called Bundle Adjustment on a Graph Processor. And there's also another long discussion paper about the general idea of a class of algorithms which I think is really suitable for this, which is belief propagation. So certainly not anything I've invented, but something which I think might very much come back into interest because hardware has changed. So we've been able to show concretely in this paper we'll show at CVPR that we can implement a classical computer vision algorithm, which is essentially, you know, the core SLAM problem of how do we jointly estimate the positions of a set of cameras and a set of points on an IPU chip by using Gaussian belief propagation. So if I just skip to the right part of this, if you're familiar with factor graphs, so on the left here, we see the factor graph for a bundle adjustment problem, and we map each of those nodes, variable nodes or factor nodes, onto tiles of our IPU, and then we're able to perform the optimization that we need to do in bundle adjustment by message passing. So we're going to send messages around between these tiles in some pattern and show that we can achieve optimization of globally consistent things by purely local computation and message passing, and show that we're able to do that very fast and very efficiently. And in some very kind of preliminary results that are in this paper, we show we can optimize, you know, a reasonable sized bundle adjustment problem 20 times faster on an IPU than you can on a CPU using Ceres, the standard CPU algorithm for that. Okay, so I think I'm pretty much out of time. So let me just finish with some conclusions. So spatial AI research, I think it's a fantastic thing to work on, and I think we'll be working on it for a number of years yet. So you know, it involves computer vision and robotics, deep learning and representations, but really focused on, you know, how can we put all of those things together to enable incremental, efficient scene understanding, taking into account also ultimately how we will lay these things out on hardware. So co-design of processors, sensors, and algorithms, I think is super important. And as I've mentioned, graph-based algorithms for estimation, such as belief propagation, and also graph-based machine learning, something I haven't really worked on much yet, but I think is clearly going to be a key part of this. So I'd just like to mention my affiliations. So I'm leading the Dyson Robotics Lab at Imperial College. I'd like to thank all of my colleagues there, and also my collaborators at Dyson who support us. So this is an academic lab with postdocs and PhD students, and we really do long-term research, academic publishable research on SLAM, scene understanding and manipulation. And finally, to mention SLAMcore. So the SLAMcore is a London-based startup which I co-founded with other previously academic colleagues, and we work on applied spatial AI solutions. So thank you very much.
Thanks, Andrew, for the inspiring talk. I loved the entire talk. I loved the amazing results and videos, of course, but I also really appreciated the vision and the broad perspective that you gave on the entire field of perception, which I believe is a great, service for the community. So giving this kind of vision and perspective. So I'm sure that in other circumstances we would have a standing ovation here, but for now we'll have to settle for a virtual round of applause. So thank you so much for giving this presentation. The plan for the final portion of the event is to have an interactive discussion with Andy. And this will happen with the help of our panel. I'm Luca Carlone, I'm assistant professor at MIT, and I will be moderating the panel together with Jeanette Bogg from Stanford. Hi, Jeanette.
Hi, everyone.
So joining us today, we have our guest panelist, which Alberto already introduced. He's John Leonard from MIT. John, thanks for joining.
My pleasure.
And also we're going to have Marco Pavone from Stanford and Alberto Rodriguez from MIT. Moreover, we'll get some help from our amazing collaborators, including Heng Yang from MIT, Ransalu, Sina Nayaki from Stanford, Nima Fazeli from MIT, and Rachel Holloway, who will help us collect questions from the audience. So I invite the audience to post comments using the interface on the event website. And I see that there are already many questions flowing. And I also invite the panelists to use the raise hand function to ask questions on our side. So of course I have a number of questions and curiosities that I would like to ask Andy, but I will actually invite John Leonard as our guest panelist to start with remarks and questions. John, take it away.
Thanks, Luca. Andy, wonderful talk. I have dozens of questions myself. I'm so excited to see this really this 3 decades worth of work. I remember, I think it was in 1999, I was an assistant professor and Andy sent me an email. He was a postdoc in Japan. And we started a conversation that's now gone for 30 years. And I'm reminded of Amara's law, which says that we tend to underestimate the impact of a technology in the short term. We tend to overestimate it in the short term, but underestimate it in the long term. And I think that's kind of really where we are with visual SLAM and spatial AI, that I think in the very long term, decades from now, this technology really can be ubiquitous to make life better for lots of people. And we've come such a long way, but there's a long way more to go. And picking amongst the many topics I might ask, I'll go to the question of robustness. I've always dreamed of having apt-get install SLAM, so that, say, someone working in manipulation, maybe mobile manipulation, they might just have this competence of knowing what is where in the world, that spatial intelligence. That's something they could just kind of take for granted and trust. And so I'm guilty myself. In the lab, we make wonderful videos and but how do you make a system where you could be blindfolded in your lab and you would say, John, I'm going to press go and I'm going to leave or close my eyes, and you knew it would just work. Where's the elusive robustness where you could truly trust 3D object-based SLAM for say manipulation?
Yeah, great question. So of course, yeah, I agree that there's such a massive gap between the thing you see in a paper, the cool video of the style that I've showed. In my lab, I've generally tried to go one more step than that, which is the live demo. So I've always been very keen on, going to a conference. Ideally,
to your great credit, which I'm a big fan of.
With a laptop and wave a camera around and show something people can actually interact with. But there's another huge number of steps beyond that to actually real product. And of course, I've experienced that with my work with Dyson. So just the amount of testing and just basic engineering that needs to be done. And I still haven't seen any indication that there's any magic bullet there. I don't think. Massive amount of testing, finding all the problems and edge cases. So of course we have some hope that, you know, things coming in, such as, you know, learning can be very important parts of improving robustness. So as we probably all know, you know, this general idea of image correspondence is probably always the you know, data association, as roboticists call it, is always the hardest part of SLAM. And clearly we see now that you know, learned mechanisms are able to do a lot better in that. But now maybe we're in this trap of you know, how do you know that your data set that you've trained on fits the place that you're actually going to test in? And that's something that I've actually got a bit frustrated with recently. So actually some of the things I'm most excited about at the moment are, you know, going towards sort of unsupervised or self-supervised learning. So actually, for instance, you know, if you want a neural network to segment the objects in a room, yes, you could have a neural network you've trained for semantic labeling in some other scene and you can test it, but it may not work that well. I think what you really want to do is get data in the space that you're actually in and learn as best as possible in that scene. Of course, you won't have high quality labels necessarily, but I think you can go an awful long way with unsupervised learning, and then maybe there's a fairly small amount of labeling needed at the end to actually relate what unsupervised learning has learned, which is more or less clustering, and relate that to you know, labels that a human would understand.
I agree with you. Just a quick follow-up, and then I'll turn it over to others. In his 2019 ICRA keynote, Yoshi Bengio quoted Buteau saying, "Nature doesn't shuffle the environment." And I think something that we can offer the machine learning community is that this, you know, self-supervised vision, or just that an agent that's controlling its own motions and moving through the world with a notion of space and time. It's a bit like having the cards in a playing, you know, in sequence versus, you know, ImageNet just pulling randomly from the internet. You know, disparate. And I think that's notion of spatial context, that is the path, because even though machine learning has obviously made incredible strides, I worry about where we are on the ROC curve, that we're very far from very high probability detection and very low false alarm systems that we could use, for example, for autonomous driving in highly dynamic environments. And so the robustness in I1 is sort of the perfection point on the ROC curve where we really know we can trust it. And so, but I think a lot of these methods you've mentioned about object-based representations and new types of processing, the message passing, it all fits into, I think we've got much more great work to do, and thank you.
Thanks.
Thank you very much, John, for your question. So I think we're going to now take on some of the great questions, and there were actually many from the audience. So Hank, you have selected one question from the audience. Can you give it to?
Okay. Yeah. Thanks, Andy, for the nice, you know, talk about perception, vision, and SLAM. But I have a very highly ranked question from Harman Purohit that asks that besides, you know, rather than solving SLAM as a standalone problem, what are the new developments in active SLAM, in particular with control and planning in the loop as well?
Yeah, great question. So. No, I mean, I'll put my hand up straight away and say it's not something I've worked on very much. And for a lot of my career, you know, the output of the work has been, you know, this is the video, this is the map, this is the camera trajectory that we've estimated. But very clearly, that's not the end goal. The end goal is embodied intelligence, manipulation. And as you see, we're really trying to work on those things now. So it has to be said that there hasn't yet been much feedback in any of the things we've done from the action to actually, you know, improve the representation. So we scan a scene, we get the representation from vision, and then we act. But clearly, you know, once you start touching the scene, understanding the physics of how things move, then that should really improve your perception and feedback on it. So I'm really interested in going in that direction. So for instance, bringing physics simulation into the perception system is something I'm very interested in. So in the system I showed you with, you know, a pile of objects that the robot was going to interact with. So when we're estimating the positions of those objects, we do take account of the fact that the objects shouldn't be intersecting each other, but we could go further and for instance say, well, physics says that this object can't be floating in the air. So there must be another object kind of right underneath it, which is supporting it. So bringing that kind of physics into the actual estimation of what's going on, and then hopefully then rolling that onwards. So as the robot then starts to interact with the scene and maybe poke one of the objects and sees how it moves, you know, we may get some kind of force information from the robot, but we'll also get some updated visual information. But then we've got to come up with a new estimate which is still consistent with physics. I think those things are very hard because simulating physics of contact is incredibly difficult, and we've tried lots of you know, different physics engines and so on that have different strengths and weaknesses. But yeah, those are directions I'm really interested in, but can't claim too much progress so far.
Okay, looking forward to it.
Alberto, you have a follow-up on this one.
Yeah, I wanted to follow up, Andy. So if you bring physics into the estimation loop, would you still call it the spatial AI, or would you have to change the name?
I'd still try and claim that name, but I don't know. It's up to everyone else whether they accept that. I think so. I think embodied spatial intelligence involves all of those things. It's about all of the sort of sources of information, sensing, and priors that you know, an embodied agent needs to use in order to understand enough about a scene to do intelligent things there. So, but based on that definition, I think it still fits.
Right. Thanks. So I was actually also a follow-up question. When you were grasping the objects, they did stay in the gripper. Did you not take any visual information into account to track it?
So we, you know, to be honest, we're doing something fairly, you mean once they're actually grasped?
Yeah, and then they're moved into the box. They were actually moving with the gripper.
They were wobbling a little bit, do you mean? Or?
They were just like being transported, right? But I wasn't sure if this was actually tracked visually.
No.
Or...
So at that point, we were assuming that, you know, once we grasped the object would stay in a fixed configuration relative to the hand, and until we place it. But certainly that might be possible.
Right.
I mean, it's difficult with the depth camera on the hand because the range of the depth camera is normally you know, the minimum range is such that you can't necessarily get an accurate measurement of something you're actually holding. Right. But you know, cameras are cheap. Maybe we just put more cameras, one right there, kind of in the palm or something.
Yeah, that would be great. Ransalu, you picked another question from the audience.
Yeah, so thanks for the talk, Andy. So I'm really excited about all the new developments, and this seems to be an evolving field. So we have a question from Carney. Is there an accepted grand goal for SLAM, upon reaching which we can comfortably say SLAM is solved? Or do you think it is continually evolving, or are there any like standard challenges for SLAM?
Yeah, I mean, going back to, you know, the question right at the start of the talk, yeah, people have been saying SLAM is solved since 20 years ago, and I think John have always been among the people that have said, hang on, you know, I'll immediately give you a way to make it more difficult, like try and do it with a single camera rather than, you know, a laser rangefinder on a 2D robot, for instance. So I wouldn't want to set a kind of fixed target. I mean, I think for me, the targets now are really about, you know, in embodied intelligence. That's what we're trying to get to, and what we call SLAM has to be a means to an end. So, you know, it could well be that a lot of the things we've done are, you know, many of them are not good enough, but some of them are overkill. So, you know, for instance, accurately estimating the metric shape of a building that's 100 meters long probably isn't really needed from many intelligent things that you would do within that building, or, you know, mapping a room with 5 million surfers, especially the parts of the room like the ceiling that you're never going to be interested in actually interacting with. So I think the way that we should measure the performance of these systems should ultimately be much more about the end goal, actions and intelligence that they enable, and then we should feed those back into how the SLAM systems work.
If I can follow up on that, I think that an easy, in quotes, an easy goal is just to see a SLAM system or a spatial perception system to be as capable as a human perception system. So whatever like a human can answer using sensor data is something that we expect for a robot, for a smart robot to answer. I don't know if it is a definition which is really actionable, but I would love to be at that point.
I mean, of course, there's many things current SLAM systems that can already do that are far beyond what humans can do. Like tell me the precise distance between those two walls, and your SLAM system will tell you within a millimeter. But yeah, clearly many things that humans can do with their spatial perception SLAM systems can't yet. So I think that's useful, and of course it's always an inspiration. And I think that I've realized more and more that I think I'd always thought, the only thing I'm interested in is making systems that work. But I've realized more and more that I think I am also quite interested in understanding how something about biological intelligence works. And I would never claim to have any expertise on that, but I just have a feeling that if we discover, representations and computational patterns that enable really generally useful SLAM systems to work that are also efficient, I think we may also learn some useful things about other sorts of embodied intelligence.
Very cool. So that is going to be like a much longer discussion, but since we have many questions from the audience, I will maybe call out on Nima to ask a question from the audience.
Great, thanks. So we had a question regarding memory. So as you get these more interesting, more high-dimensional maps or with the semantic information, if you're having an embodied AI and an agent that is supposed to move around and be untethered, how do you think we can overcome the challenge of memory and capacity for maintaining these maps?
Yeah, great question, and something we've thought a lot about. So I think the key is, introspection and abstraction. So this is actually something we're concretely working on now, kind of in the graph processing work. So we've got this computational resource. Maybe it's an IPU chip that is able to basically process a certain size of graph. And clearly, if a camera keeps moving, mapping more points, the graph we're interested in is going to get bigger and bigger. But I think that what we can do to overcome that is always be looking for ways to simplify the graph. So for instance, if we've mapped 100 points, and at some point we realize they all lie on the same wall, and maybe that information comes from a neural network that's telling us it's recognized a wall, or maybe it's just pure introspection that we keep finding all those points are really planar. We could replace all of those nodes in the graph with a single plane node that abstracts and captures all of the relevant information, and then reconnect it to all the necessary places. So I kind of think that must be how scalable memory works. So you've got a lot of detail about the things you're looking at right now, and then the things maybe the things you're not looking at right now, they fade down to something more abstract, which is still sufficient for them to be useful, but is much more efficient.
And I guess the semantic understanding can also guide, what to compress, and can inform how to compress things in the past. That's definitely
absolutely, yeah.
So I think Rachel picked a very interesting question from the audience. Rachel, do you want to read it?
So Lucas Manueli asked, how should the output of spatial AI systems be different, if at all, for different downstream applications, like manipulation versus self-driving? And I think a related question from Emmanuel Franz was about how would you integrate semantic integration with NLP or human-machine interaction in the context of these different applications?
Okay, so let me take the first one. So this was about how might the output be different for different applications. Yeah, so it's a good question. So clearly different applications need different capabilities. I think one of my hypotheses is they might not be completely different. So this may be more of a sort of continuum. So I imagine there might be, a relatively small number of performance parameters that are defining how well your system works. Let's say the accuracy that you can measure pose might be one, the density of reconstruction, the level of fineness of your semantic labeling, the precision within which you can predict the time to contact of that point that's directly in front of you, or something like that. Maybe there are a relatively small set of kind of system defining parameters like that, which each different application would have different positions on those sliders. So a drone needs to be able to react to really quick changes, but in some other regard, it might be it doesn't have to deal very much with objects or something like that. Whereas a home robot has different. So I kind of hope that there'd be relatively general sort of architecture for spatial AI, which then you would specify a set of kind of performance requirements for a particular application, and the algorithm would hopefully configure itself for kind of optimal performance with regard to those parameters. So could you remind me about the second question?
Yeah, the second one's about integrating in with things like NLP and human-machine interaction.
Yeah. Sure. So another area that I really haven't done any concrete work on, but is absolutely important if robots are going to be working alongside people. So the only kind of concrete thing I can say is that as I think we step up in spatial AI towards these more semantic and abstract representations, we're going to have much more ability to be able to communicate those representations meaningfully to a human. So even when you watch a robot vacuum cleaner now, it's sometimes frustrating. I must admit, you want to do things like tell it, go back to the kitchen, it's still dirty, or point over there and say, go and spend a bit more time over there. So it would be fantastic if they could understand those things. So yes, I guess if you imagine a set of queries like that of actions, like go back to the chair behind the sofa and clean under there, and think about are the representations that we're building, which will hopefully be abstract and hierarchical, do they, so these scene graph like representations, do they enable those kind of actionable queries?
Thank you, Andy. Fascinating discussion, fascinating talk. I really loved your historical perspective on the SLAM problem. Unfortunately, it's time to wrap this up. On behalf of all the co-organizers, Luca, Jeanette, Alberto, I would like to thank everyone that has joined us today for the inaugural talk for the Robotics Today talk series. Next week, we're going to have another exciting talk from Leslie Kebling from MIT on recent advances in decision-making and reinforcement learning. Importantly, this talk series is really an experiment on online robotics community building. Our goal here is to view virtual talks not as a backup option, but really as a new opportunity to achieve a broader reach for excellent talks such as the one that Andy gave today. But we want to get it right, so it's very important to us to hear your feedback. So please go on the website, spend a couple of minutes, and provide us with any comments you might have on how to make the seminar series more effective, more useful in general. Great, thank you very much, and I'll see you next week.